For those who are just joining us, I see Dave Doman's online as well. Thanks, Dave, for joining us. We are now going to turn the time over. Oh, Dave, you want to introduce yourself? Go ahead.
Oh, no, I just wanted to join to see the control allocation portion, which I think I'm on time for here. So,
Great.
Anyway, I've looked at Doug's work here over the past couple of years when he was at AFRL and followed it with some interest. And I serve as the Control Science Center Director back here at AFRL. That's about it.
Great. Thanks for joining us. So unfortunately, Brian Holmhansen, who is the sponsor of this project from ONR, his flight was delayed, well, canceled last night due to weather out of Dayton. But he should be arriving any minute. So hopefully he'll be here this afternoon. We've been going over this stuff for the last 4 or 5 hours since about 8 o'clock this morning. And our next presentation is by Zach Montgomery. Again, Zach is a PhD student, just graduated, now works at Area I. And Zach, we'll turn the time over to you.
Thank you. Sorry, I can't turn my camera on, and sorry if there's a little bit of background noise. I'm in the best location I can be. Let me share my screen. Okay, here's my screen. So let me share that. So there were 2 different approaches to control allocation that were attempted. The first was analytic. We've kind of already gone over that a little bit. Now I'm going to go over a general numerical approach to control allocation that we implemented on the Horizon aircraft. It's a method that uses a control mapping methodology that I'll go over here. So the general idea here is we can use an aerodynamic tool and tie it together with a nonlinear optimizer. And then we can run optimizations that will determine what the control surface deflections need to be for a certain flight condition and to optimize for some objective function. So usually what we want to do is minimize drag while constrained to a certain flight condition. So after we get the aerodynamic tool coupled with the optimizer has control over all of the control surfaces on the aircraft. And then it might be constrained to a certain lift coefficient, to a certain rolling rate or something like that, while trying to minimize drag. That one optimization case would be one point in a larger data set. And so you would repeat the optimizations for a wide range of flight conditions that you would expect. Then after you've done all that, you have a large database of optimizations. That database you could then use in flight. You could interpolate within it. You could use the different flight variables that were the constraints during the optimizations. You could measure those in flight and use those to interpolate within that database and pull out the desired control surface deflections. However, that can be fairly difficult to do in flight, especially with the small flight computer that we have. So we like to condense the database down and make mapping functions, which are so we basically just want to curve fit the database down, and I've come up with a multivariable polynomial that does that fairly well. Then after we do that, this mapping function will take the place of the database. It acts as the control allocation task, where you receive in the commands from the pilot, which would be like your desired flight variables and other sensor ratings. And then your mapping functions would spit out what your desired control deflections are. Since I use this curve fitting technique, and sometimes the database can have a large number of independent variables, the curve fitting method needs to be able to handle an arbitrary number of independent variables. So I came up with a custom code to do that. It has two options that you can implement. You can do an automatic polynomial fit technique, where all you have to do is specify the maximum order, the max exponent you want on all of the independent variables, and the routine will automatically determine which polynomial coefficients work best for your data. This automatic polynomial fit routine was developed by Morelli. I implemented it, and the general procedure of how that works is it provides a balance between the goodness of the fit measure and a predictive capabilities measure. Another option is you can just specify the size of the polynomial. You can specify the max order, that max exponent on each independent variable, and then just perform the manual fit directly, which runs a lot faster and is a little bit smoother. You have full control of all over the symmetry constraints, which I used pretty heavily when doing all this work. And this animation on the left just shows some example data, my attempt to try to visualize 5-dimensional data. You have a 3-dimensional plot. They spin just because 3-dimensional plots are kind of hard to see on a screen. And then it loops through the third independent variable. So we have pitching moment and rolling rate on the horizontal axes, the actual deflection on the vertical axis, and then it just loops through different CL values. Once we have that, I implemented the control mapping methodology on 2 different aircraft. I'm not going to go over the VCCW here. So this was done previously with the Air Force. For ONR project, we implemented it here on the Horizon Flying Wing. It was built in-house. It has about a 10-foot span. It has 11 different control surfaces. We played around with the idea of using morphing control surfaces that would vary smoothly across the span, but we decided to go with discrete. Yeah, so there's the aircraft there. It does have 11 degrees of freedom, 11 control surfaces, 5 on each semi-span and 1 in the center. So the first control mode was not implemented using that mapping methodology. Mode 1 is meant to be a safety mode. It essentially behaves like a large set of elevons, which is a combination of elevators and ailerons. It's pretty typical for flying wings. And the purpose for this is for when we flight test, we have a safety mode we could revert back to where we know how the aircraft is going to behave for a given set of pilot commands. The first mode 2 is the first one implemented using that mapping methodology. The goal here is to control roll and pitch while minimizing drag. For each one of the optimizations run for mode 2, there were 3 constraints. Constrained to a certain lift coefficient, constrained to a certain pitching moment coefficient, constrained to 0 rolling moment constraint. The optimizations were run for a wide range of lift coefficients, pitching moment coefficients, and non-dimensional rolling rates for a little over 6,500 optimizations performed. Then I condensed that data down using the automatic fits feature, and I fit the data directly to each control surface deflection. The animation shows the results for mode 2 for various pilot commands and for various CL values. This plot is shown as if we were looking at the trailing edge of horizon if we were standing behind horizon. So the left wing would be on the left, right wing would be on the right, and positive deflection is a trailing edge down. So this is what it would look like if we were standing behind horizon and playing with the transmitter. Mode 3, so this animation is the same. It's as if we're standing behind horizon. Mode 3 is exactly the same as mode 2. It attempts to control roll and pitch while minimizing drag. However, it has an additional constraint done on all of the optimizations, and that constraint is an additional 0 yawing moment constraint. So in theory, mode 3 should behave just like mode 2, except whenever we roll, there should be there should be neutral roll yaw coupling. Ran this for a wide range of lift coefficients, pitching moment coefficients, and non-dimensional rolling rates. And the reason we have the multiple modes is so that we can work our way up. But when we flight test, we can work our way up to the higher modes and implement things more gradually. Mode 4 builds on mode 3, except now instead of a 0 yawing moment constraint, there's just a given yawing moment constraint where mode 4 attempts to control all 3 axes, roll, pitch, and yaw while minimizing drag. Ran this for a large range of data, including a span of yawing moment coefficients. The introduction of yaw is quite a bit tricky. And so I had to play around with the optimizations quite a bit to try to get them to converge to similar answers throughout the database or the design space, which is why there's such a large number of cases for mode 4, just under 60,000. Then I curve fit that using my custom multivariable polynomial fit routine. And you see the results here. When it shows green, that's like a pitch only maneuver. Purple would be like a change in the lift coefficient. Blue is roll only, and red is yaw only. And so you can see when it's red, it splays or it alternates the deflection between neighboring actuators. So it does something very draggy. You can see here, it'll come up again. It'll do a right yaw, then a left yaw. And so, and again, you'll be able to see that on the aircraft when they do that. So we're pretty happy with that, or hopefully it'll behave well in flight test today. So that is mode 4 control mapping. Do you want me to go into this, Dr. Hansager?
Yeah, I think so.
So we did a quick comparison to see how various aircraft compare for yaw authority, specifically how Horizon compares. The VCCW was the previous aircraft that I did a control allocation on, where we tried to control yaw from the main wing, but we used a morphing. We used continuous control surfaces, which don't have any span-wise gaps, and that turns out to be pretty bad for yaw authority. We estimated the max yawing moment for various other aircraft that have a rudder and compared that to Horizon, as well as for the B-2 Spirit, which is the only other flying wing aircraft we could find that actually has yaw control. There's various other flying wing aircraft, but they don't have direct yaw control as far as I could tell. And the B-2 Spirit, it controls yaw through this drag device, the split flap aileron. And you can see that we're in the same ballpark for max yaw authority as the B-2. However, the B-2 likely uses differential thrust to help augment its yaw authority. So our comparison here is only to the aerodynamic yawing moment generated by the split flaps. We're pretty happy with that. We think that's pretty nice. So we'll see how well it does actually flying today. And then I have some flight test videos, but I think Ben has that prepared as well. Are there any questions on the control mapping methodologies or any of the modes?
Questions?
I've got a question, Zach. This may seem kind of silly, but I'm just curious. You probably went into developing mode 4 with certain ideas as to what it would look like. I'm just curious if there were any surprises when you know in making this figure right here. Was there anything that surprised you as far as, you know, I didn't expect it to look like that when it was doing a hard roll or something like that. Does that make sense?
the red animation for the yaw only, I'm pretty pleased with that. That's what we expected. And that's based on our intuition from, or what we know from when I worked on the analytic lifting line stuff for yaw. Anything that has high drag, high frequency content is going to be good for yaw, and we see that here with the alternate deflection on the one wing. It's going to generate a lot of drag. So that is good. That's kind of what I expected. For the roll, it seems a little weird. So when it loops back around to blue, that's a roll only command. At first glance, that seemed a little odd to me. Why would it not just deflect like it did in mode 2? But what you have to remember here, that's a roll only command, and the yaw is set to 0. So it's trying to do that roll maneuver with 0 yaw. And so it's the same thing with mode 3. Whenever it does a roll maneuver, it's trying to do that with 0 yaw. So on the upward deflecting control surfaces, it tries to make those more draggy than the other side. So after a little bit of thought, it makes a little bit more sense.
Thank you.
Hey, Zach, is Dave Doman. Just one comment. It looked like when this thing's generating a lot of yaw control authority, it's doing it by directing adjacent control surfaces near the tip in opposite directions, which is kind of like generating differential drag with split flaps on the B2 example that you showed.
Yes.
I mean, you don't have split flaps, but the next best thing would be to deflect the most outboard surface in the opposite direction as the next most inboard surface, right?
Yeah, and that's definitely what we see here. And I don't think you were logged on when I went over the analytic work, but I'm convinced from the analytic work I've done and from all of this that if you're constrained to control yaw just from the main wing, the best thing you can do is a drag device at the wingtip. Or if you could have something extend out past the wingtips, that was a drag device, that's the best thing you can do, because it's going to generate the least amount of drag while still doing the yaw maneuver.
All right, thank you.
Yep, and which is kind of a surprising statement, because we know with certain lift distributions, you can generate induced thrust on certain sections of your wing, which would be very good for yaw, but for just yaw only, for just the yaw only maneuver, the best thing you can do is just a drag device as far away from the CG as you can. Any other questions?
Zach, I have one really quick. If you go back one slide, for modes 2, 3, and 4, you're holding 0 rolling moment. So that makes sense. You're essentially reached a steady roll rate, is what you're saying.
Yep. So they're all constrained to 0 rolling moment coefficient, meaning there's no, so each one of these p-bar values is like a steady rolling rate, and that p-bar value is connected to the roll input on the pilot, on the transmitter. So when the pilot sends a command, it's like he's commanding a steady rolling rate. Yes.
Right.
And so we're ignoring the roll transient.
Okay.
Yeah.
And that was my question, is that, and I mean, probably it'd be something that we'd have to ask Dave about, the pilot, right? But like, I don't know. I just had that thought that I know that transient is pretty short, right? But,
yeah, the roll transient time
it.
is usually really short for most aircraft.
Yep.
And Horizon's no different.
Sure.
And because of that, most pilots associate roll commands with roll rate. They don't even notice. So,
Great.
yeah.
Okay. Great.
So that's not necessarily true for yaw and pitch, but it is for roll. Yeah, so we could have created all of these control mappings using not assuming that, and we just would have had more constraints, and then we would have had a range of rolling moments here, and then the pilot would have controlled rolling moment instead of rolling rate, and we would have measured rolling rate. We could have done that, but that would have complicated things. It would have made a lot more optimizations needed to be run, and then the curve fitting would have just been more difficult because it's a higher dimension, but it could have been done.
But it'd be interesting to see if it varied very much doing that. My guess is probably not. It'd probably be almost the exact same deflections.
Yeah, I think so. We do know from the analytic work that the optimal twist is different for roll initiation than it is for steady rolling rate,
Yeah,
or for any other like mix, so like a transient period. But it's such a short time period we're talking about that it doesn't really matter. And our mode 2 flight Monday behaved very well, I think, in row.
yeah, yeah.
So, and the VCCW aircraft was designed the same way, and it behaved very well in row as well. So,
Thank you.
One other question, Zach, is there any observations on how well these control allocation methods allow you to execute coordinated turns? What you really want is zero stability axis yaw rate and some finite stability axis roll rate. So another way to put it is that if you had a ball instrument, a turn and bank indicator on there, the ball would be centered when you did the turn. So any observations on that?
we have so far only been able to test up to mode 2. Later today, they're going to flight test mode 4. And so we will see how well it behaves today in flight test. I'm not sure if they plan to test coordinated turns. I assume they are, but I think we're limited on the actual amount of flight time we can actually test in mode 4. So I think they were hoping to show yaw control through flat turns. They might do some coordinated turns, but I don't know if we have anything on board that can measure that so that we would be able to prove it.
Yeah, well, if you've got a accelerometer package on board, if you're seeing a lot of NY, that would indicate you're not coordinated, right?
So we do have a Pixhawk on board, but it's been through a couple different crashes, and it's kind of questionable how well it's behaving. So we might get data, we might not.
Yeah. All right, thanks.
Dave, that's a good question. I want to comment on a little bit more. So what Zach has come up here with for this controller, actually, if he goes into mode 3, if you just switch over to mode 3 here, Zach. So this is creating roll. So when it rolls, it tries to get rid of any adverse yaw. And that does not ensure, though, that you are coordinated in a turn, right? So when pilots coordinate a turn, they're actively controlling the rudder to take out any of their NY, right?
Right.
So the ball stays in the middle. So the pilot that we have, he's a very skilled RC pilot, and he can fly, he can coordinate turns on a traditional aircraft. On this aircraft, we have maybe a total of 8 minutes in the air right now. And so he's flown it every time, but he's still getting to know the aircraft. And so although the authority is there, we believe, to coordinate the turn, we're not sure that we have the sufficient instrumentation or really the experience of the pilot to be able to coordinate that from the ground. Does that make sense?
That makes sense. Yeah.
So we're not sure what we're going to get out of this, but the short story, I guess, or the short answer is that no, we haven't looked at coordinated turns specifically. So
yeah. Okay. Thanks.
I would add to that and say, if we do prove we have yaw authority, and it's pretty decent yaw authority over coordinated turns and various pitch maneuvers, if the yaw authority is there through every mode, then it's just a matter of the pilot implementing the proper amount to coordinate.
Yeah, we do expect, I guess we're hoping, and we'll see how it goes in flight test today, that when he's in mode 4, see if he doesn't touch the rudder in mode 4, it's identical to mode 3. Basically, the rudder is held at the rudder stick is now a yaw input instead of a rudder input. And so when it does begin to bank, it's going to naturally try to take out any yaw according to this model that Zach has come up with. So we are interested to see in mode 2, he's flown a few figure eights in mode 2. And so he has an idea of what that feels like. When he goes to mode 4, when he flies those figure eights, even if he doesn't touch the yaw stick or the rudder stick, we're interested to see if he notices a difference in those turns, because they should be closer to coordinated, possibly. So we'll see if he notices any difference there, but.
Yeah, all right, good.
And Zach, so when you create the yaw, so I think it makes sense to use the last two, the ailerons toward the tip, but the very last one has very narrow kind of span. So maybe second and third one, if they use those, maybe even though the movement arm is shorter, but you can create more drag with those. But
So the
he's trying
drag,
to use the first and the second ones still.
so the drag really happens between the two actuators when they're deflected separately. So when you have the two outboard, even though they're small span wise, you're going to get a lot of drag between. And so that's kind of why they have smaller span wise length out at the tip than they are at more towards the root. I believe that helps with yaw authority.
Okay, right.
Okay, thank you, Zach. Appreciate it.
No problem.
I want to thank you specifically for taking time out of your work schedule there to present. Like I said, Zach has graduated a couple weeks ago. He started at Area I this last Monday, so they were kind enough to let him take some time out of his schedule to present. So